Well, okay, so it could get into a loop, but it's making a random decision every time. So would it be infinite? It's sort of probabilistically, Anybody else, any other thoughts? Yeah.
We're wasting a lot of resources where if you actually implement proper patterns, then you don't have to keep sending new frames. You've done that before.
Yeah. So it's wasteful, right? Like it's sending over links it doesn't need to, and just thinking about it, like how long will it take this packet to get to its destination if you just make a random choice at every step, right? Like who knows, right? It could take any amount of time. Similarly, you could have a router that just sent a packet to all of its neighbors. And if its neighbors send it to all of their neighbors, and so on, with a caveat that we'll get to in a future lecture, that should work too, right? So why wouldn't we want to do that? Why not just send it to everybody? Yeah?
It congents the wires pretty quickly.
Yeah, so it's just super wasteful, right? You'd end up sending the packet over every link, no matter where it's going, and you could probably just send it over a subset of paths, or of links, right? Meaning on a path. And so finally, another part of this challenge is we want our routing to be able to adapt to arbitrary topologies, because the graph that describes a network can vary a lot. For example, this is the topology of UUNet. UUNet was a carrier network, meaning that it's a communications provider. And specifically, it was what's called a Tier 1 provider, and I think we'll probably talk about more exactly what that means later in the semester, but sort of like the first order approximation, it means that they're like an ISP for ISPs. Today, they're part of Verizon, but you can see, there's a lot of links, kind of messy, gathered around major cities. CenturyLink is another big ISP, and this is kind of what their North American network looks like. Berkeley's network, a little bit more structured, looks something like this. With, residence hall over there on the left, various other things up at the top is how it connects to its ISPs. Enterprise networks kind of have their own thing going on. They often have like a head office and several branch offices. Data center networks often have these very regular structured topologies, something like this. These things are really engineered, and they're sort of, engineered without the constraints of, like geography and populations and so on. Of course, the internet as a whole is sort of a mishmash of everything, right? Because it's, like a network of all these networks. And so, in all these different networks, we might actually use different routing algorithms. But it's still generally good to have a routing algorithm able to adapt to any topology. And this is especially true because every topology is dynamic. They all change. And so why is that? When I say that every topology changes, why is that? Yeah? Any router can go down, right? You always have to deal with failures, right? Somebody could put a backhoe through a link, or the power could go out where a router is connected, anything like that, right? Another reason why, lots of networks are dynamic, because you might want to add equipment too, right? You might want to say, oh, well, we need more bandwidth here, so we're going to install new links. We have new customers, so, we're going to have to adapt to those customers and so on. But, everyone has to be dynamic because they all have to deal with failures. So, taking a step back from routing, let's talk about one of the other challenges that routers face, and that's the challenge of forwarding. So when a packet arrives, for example, at R2, so a packet arrives at R2. R2 is going to forward it to one of its neighbors, right? It's going to resend it. And so you need to decide which neighbor are you going to resend that packet to. And you want to be able to make that decision fast. Remember, like, packets can arrive on the order of nanoseconds. So this sort of implies that whatever decision making that you need to do when a packet arrives needs to be really simple. And so almost universally, the solution to this is that these devices just use a simple table lookup. So here's a network. R2 might have a table that looks something like this down at the bottom. For every destination, there's a row. And in that row, there's a column telling it which neighbor to use to get to that next destination. That is, like, what the next hop is. For example, if R2 gets a packet for B or C, it's going to send it to R3. Any questions on this? All right. Now, at like a low level, right, eventually it's going to need to figure out which physical port to send the packet out of, right? So maybe each port has a number, which I've sort of drawn up here. And then you can create a table that looks like this one on the right. There's sort of practical differences between these two, right? This one on the right, the second column is the port number to use. But logically, they're pretty much equivalent. It's a lot easier to do examples using ones like the ones on the left. So we'll often stick to that, but sort of be aware that both of these exist. So note that the only thing which determines our forwarding decision in this case is the value in the destination address field of the packet header and the value in the corresponding row of the table. Which is to say, if the tables are fixed, then only the destination field determines what happens to a packet. So we call that destination-based forwarding or destination-based routing. And it's kind of the most basic way of doing this. And it's super common. It's one of those sort of like archetypal internet things. And we'll talk about some alternative approaches later, but you should think of this as the default. So taking a step back, we'll look at the two things we know routers do, forwarding and routing. So forwarding looks at a packet's destination in the table and sends the packet to the neighbor given in the table. Routing, on the other hand, has routers communicating with other routers in order to determine how to populate that table that you're going to use for forwarding. That's how that table gets set up. So forwarding is inherently local, right? It only involves the arriving packet and the local table. And so, that is, if a packet for host B shows up at some router, all you need to do is look up B in the router's table, and you know where to forward the packet. Routing, on the other hand, is inherently global. In order to have figured out what R2's table entry for B should have been, you need to know something that's not local to R2, right? You need to know where B is, and B isn't local to R2. So Sylvia mentioned this term data plane a couple lectures ago. And so forwarding is the primary role of the router's data plane. When we talk about the router's data plane, we're primarily talking about forwarding. The primary role of the router's control plane is routing. That's the primary control plane operation, is figuring out these routes. And so finally, we can look at the timescales that these things operate on. And so forwarding takes place at the timescale of packet arrivals. So that might be as fast as on the order of nanoseconds. Routing generally takes place much slower, right? You only need to change these tables when something about your network changes. So that's something like when a link fails, or when a router fails, like we talked about, or when a router is added. So any questions on forwarding, routing? Comparisons between the two? Make sense? Okay, so let's talk a little bit about theory. So we can graph the path that packets to a destination will take by if they follow the table entries. I've sort of been doing this all along, but one possible set of table entries for paths to A from R1 and R2 would look like these, right? From R1, it's going to follow this red path. From R2, it's going to follow this blue path. And so, the next hop entry in the table becomes an arrow in this graph. Notice that, because there's only one next hop per destination in those tables, there can be only one outgoing arrow per node if we're looking at it for a specific destination. And so that means, once paths meet, they're never going to split. Like here, you can see sort of two different places the paths could meet depending on what the table entries look like. So in the top, paths to A from R1 and R2 don't meet until R8. In the bottom, they meet at R4. But in either case, once those two paths to A meet, they're not going to diverge again because there's only one next hop for packets going to A. So like in the bottom, it's not like one of the paths could go from R4 to R6 and the other could go to R8, right? They both need to follow the same wherever it goes. Does that make sense? All right, so the set of all paths to a destination form this directed delivery tree for that destination. And this tree, has to cover every node. We want to make this assumption that a packet to somewhere can arrive at any router and will have a way to get to the destination. And so, technically speaking, this creates this oriented spanning tree rooted at the destination, meaning it's a spanning tree with directed edges which all point towards the root. A spanning tree is a new term to you. A spanning tree is a subgraph that touches every node in the original graph and forms a tree. That is, it doesn't have any cycles in it. Any questions on this? All right, so moving on. Earlier I said that, we wanted good paths between hosts. And the notion of goodness is flexible, but surely the minimum requirement for good must be that packets eventually reach their destinations, right? Anything else is definitely not good. So it'd be, useful to be able to reason about this. And this was articulated by Scott Shanker, who is my advisor, as routing state validity. And this is a term that we use at Berkeley. It's not a standard term, but it's a useful one. And so in order to discuss routing state validity, we need to distinguish between two different views of state. And so the local routing state is just the contents of a table at any particular router. By itself, this can't be evaluated for its validity. It needs to be evaluated in terms of the global context. And so all that's saying is, if I give you some router's table, here's R2's table, is that valid? Will packets forwarded using this table get to their destination? Obviously, there's no way of knowing from just this information, right? So the global state is the collection of all the local state. It's, the contents of all the tables across all the routers. And so this is what actually determines, which paths packets take across the entire network. And we say that the global state is valid if it produces forwarding decisions that always deliver packets. So we can think about the goal of routing protocols as computing valid state. And eventually we're going to talk about how you actually do that. But just assuming that you've got some routing state, how can you tell if it's valid? We want a succinct correctness condition for routing. So